1. Hi everyone, my name is Siamak and welcome to the ACigs webinar series. Today we are doing our webinar number 25 from our webinar series, the Australian chapter of the International Geosynthetics Society. Today is 19th of October 2021. And as you know, ACigs or ACigs is part of the global society called IGS, International Geosynthetics Society, with more than 45 chapters around the world, 4,000 individual members, more than 500 student members, and 190 corporate members. So Australasian chapter is basically covering Australia, New Zealand, and the Pacific Islands. So this slide shows you the Geosynthetics Society website, IGS website. So when you become a member of this society, you will get access to all of the technical resources, the events and networking, and all the activities that the IGS normally have around the year. And then this one is showing the ACigs website, which has been refreshed this year. So you can see all of the upcoming events, all of the information about membership for the ACigs. If you want to join as an individual or as a company, all the information is on the website. Also our events, and we have good resources also available, technical resources available on the website. And as part of those technical resources, you will get access to the recording of all of our 25 webinars which we've done so far, and also a number of other events that we have recorded, and the video is available on our website. At the end of this webinar, if you need a certificate of attendance, you can send an email to info@acigs.org, and then we can organize this certificate for you. And today's webinar, we firstly thank our sponsors for this event. Naue Asia is the sponsor of today's webinar, so we thank Naue, and Jake is representing Naue Asia in this webinar today. We will ask Jake to provide us with a very quick intro about the company at the end of this webinar. And the topic for today's webinar is economic and ecological benefits of using geocomposites in railway structures. And this will be presented by Jorg Klompmaker. So I'll go quickly through Jorg's bio. So Jorg is a German qualified engineer specializing in soil reinforced structures, pavement engineering, and waste management design. Jorg has previously worked with German geosynthetic manufacturer Luckenhaus, where he was involved in the development of geosynthetics used in soil asphalt reinforcement application. For the last 13 years, Jorg has been employed by the German consultancy BBG as a senior technical consultant engaged in road and railway engineering, reinforced earth structures, including embankments on soft soils, landfills, and hydraulic engineering. Jorg has a deep understanding of a wide range of geosynthetics that are commonly used in such applications. Jorg has either written or co-authored some 70 technical publications that have been presented at various technical conferences throughout the world. Jorg is a member of a number of technical committees, such as Technical Committee 210 Dams and Embankments, International Society for Soil Mechanics and Geotechnical Engineering, ISSMGE, Working Committee AK6.4 Landfill Technology, German Association for Geotechnics. Thank you. And with that, I stop share from my end, and we ask Jorg to start the presentation. Thanks, Jorg, and the floor is yours.
Thank you, Siamak, for the kind introduction. So, as already introduced by Siamak, the topic of this presentation is economic and ecological benefits of using geocomposites in railway structures. Just to be all on the same level what a railway structure consists of, I am showing here a slide which comes initially from the International Union of Railways, and it shows the individual layers of the superstructure and the subgrade and substructure of a railway structure. So first of all, we start with the upper layer, which is the ballast layer, which carries the sleeper and the rail. Underneath, we might have a sub-ballast layer, depends on where we are in the world and depending on the requirement. And these two layers are usually called the track bed layers. So ballast and sub-ballast are the track bed layers. Underneath the sub-ballast, we usually have the prepared subgrade or a formation level. And underneath, we have an embankment or an excavation surface. Laterally, there can be a longitudinal drain. This can be on one side of the track, or it can even be on both sides. Let's look at some track substructure problems. So problems we can come across are, for example, differential settlement problems. And this is what the picture shows at the top left. The cause of this can be a rearrangement of the ballast or sub-ballast aggregate as a result of insufficient lateral confinement or insufficient strength of the subgrade. The consequence of that is a reduced service life, of course, higher maintenance cost, and even a risk of major accidents. If we have very severe differential settlements between the left and the right rail, of course, there can even be derailing of trains. What is a possible solution? We can use geogrids or geocomposites. The difference between the two I will discuss a little bit later. Another problem can be the so-called mud pumping or ballast fouling, which this picture is showing. So the cause of that is infiltration of the fines from the subgrade, which is moving up into the ballast or sub-ballast layer. Usually, another reason is insufficient filter stability between adjacent layers and high water tables, which are transporting the fines from the subgrade into the upper sub-ballast or ballast layer. The consequence of that are decreased drainage efficiencies, excess pore pressure that can threaten the overall stability of the railway track, and finally a reduced service life, which in the end means we need higher maintenance cost. Also here we can use geosynthetic products, usually to separate the soft subgrade from the coarser granular sub-ballast or ballast layer. We can use geotextiles as a simple separator, or we can use a combination of a separator and a geogrid, which we then call a geocomposite. Let's look at the functions of these two products. First of all, let's focus on the geogrid functions. A function which has been defined over the last years is the so-called stabilization function. The stabilization function is a result of the particles penetrating partially or fully into the aperture so that lateral deformation is restrained. This, of course, leads to the second function. We need a stabilization function to allow mobilization of tensile forces in the geosynthetic as a result of the loading on top of our railway structure. So with the stabilization function and the loading on top of our railway track, this mobilizes tensile strength in the reinforcement. And of course, depending on the stiffness of the product, different strength properties can be mobilized. We'll look at that also at a later stage of this presentation. Now let's look at the geotextile functions. The foremost function of a geotextile separator, of course, is the separation function. And this is all about preventing the subgrade soil intruding into the aggregate and preventing the aggregate base migrating into the subgrade. So it's not only one way that the fines are moving up into the sub-ballast or ballast layer, also the separator prevents that the coarser material is pressed into the soft subgrade. The next function is the filtration function. This restricts movement of soil particles, but at the same time, it allows water to move freely from the filtered soil into the coarser adjacent soil, which are sub-ballast or ballast layer. And also, to a certain extent, there is a lateral drainage effect, which we can quantify in geotextiles. Of course, usually the geotextile separators are quite thin, so there's a limited amount of drainage, but still it's a very porous material, and we can assume a certain amount of pore water, which will be drained laterally in the geotextile. Next, we will look into the functions of the geocomposite or the geogrid, depending on where it is installed in the railway track. First of all, we can install a geocomposite between the subgrade and the subballast or ballast, depending on where we are in this world. Sometimes there is no subballast layer and the ballast layer is directly placed on the soft subgrade. So in this case, we would use a geocomposite to provide separation and reinforcement. And the main function of this product would be to improve the bearing capacity. So always if we have soft subgrade and the formation requirements for the railway track are not met, we can use a geocomposite to reinforce and to separate. If we are already having a firm subgrade and we don't need improvement of bearing capacity, we can place the geogrid underneath the ballast or the subballast layer. And then in this case, we are maintaining, or let's say we are reducing maintenance in the track because we are reducing lateral deformation within the ballast or subballast layer. So let's look at the benefits of using these geosynthetics, the separator and the combination of the separator and the geogrid in railway track applications. So the first benefit of these products is a lateral restraint, as I already mentioned, as a result of the stabilization effect. And another effect or benefit is the load distribution. So we already can assume that there is load distribution in the track without any geosynthetic. But with the geosynthetic, we can even increase the load spread within the ballast or subballast layer. So we are reducing the stresses which are transferred to the subgrade. And by reducing these stresses, we are reducing settlements and also differential settlements, which are the most critical point in railway track structures. So as a result of the lateral restraint or the interlocking mechanism, as we also call this effect, the particles are prevented from moving sideways, and this increases the load spread. This interlocking mechanism has been tested in a large-scale test. This has been carried out at a university in Germany, in Weimar, and the test consisted of a 2.2 van, which was positioned on 4 reinforced stone columns. So initially, the stone columns were encapsulated in a wooden box, and the granular material, this was a crushed stone, was reinforced by 4 geogrid layers. I think you can see them within the stone columns. If we zoom in the picture, this makes it even more visible. You see the geogrids here. So after taking off the side walls of these wooden boxes and lifting the full weight of the 2.2 ton van onto the 4 stone columns, each of these 4 columns is now carrying the load of the van. And we can see that as a result of the interlocking between the aggregate and the geogrid apertures, which we call the stabilization, now the load is mobilizing tensile forces in the geogrid, and the lateral restraint effect really reduces horizontal movement of the aggregate. And this is what we account for as a benefit of the geogrid in railway structures. Of course, this is a worst case scenario because in the normal track, we would have the lateral support of the surrounding fill. But even with the missing support, we can very clearly see this lateral confinement that takes place as a result of this interaction mechanism. So the next slide is showing us the benefit of the geogrid in terms of an improved load distribution. On the left side, we have an unreinforced base course, a load P on top of the base course. On the right side, we have a reinforced base course, the same load on top of the base course. And in both cases, we have the same stress underneath the base course, which is then the stress that's transferred to the subgrade. But for the reinforced case, we can achieve the same loading scenario by reducing the base course to a certain percentage. Usually, as a rule of thumb, this is approximately 30% compared to the thickness of the unreinforced base course as a saving potential when we're using geogrids. So the benefit of using geogrids due to this increased load spread is that we can reduce the thickness of base courses. And that, of course, especially if good quality fill material or subballast material is not available close to the site, of course, has an environmental impact factor as a benefit for the geosynthetic solution. Next, we will look at the benefit of a geotextile separator. So as already mentioned, if the filter stability is not given between the fine-grained subgrade and the coarser subballast or ballast layer, the geotextile prevents contamination of the subballast or ballast layer with fines. We are maintaining the drainage efficiency because the pores are not clogged with fines. We are providing drainage and we are reducing the risk of frost heave. This, of course, is only valid in countries where frost is an issue, but here in Europe, definitely we want to have a good drainage efficiency of our aggregate layers, so the pores shouldn't be clogged with fines. And in the winter period, then also we can maintain the drainage efficiency and we prevent frost heave. So let's look at performance test results. So we learned already what are the benefits, but can we also see this in tests? Therefore, large-scale lab tests have been carried out. The first one is showing the improved load distribution if we are using a geogrid in a base course. So the test was carried out at the Technical University in Clausthal in Germany. We have a large-scale box test with dimensions of 2 meters in width, 2 meters in height, and 2 meters in depth. It was filled with a 1 meter soft clay layer that had a CBR of 2%. On top of that soft clay layer, we have a thin sand layer in which earth pressure cells were placed, starting at the center line of the load application area and then moving sideways. So this is only installed on one side because we have a symmetrical situation here. On top of the sand layer, we have a 40 centimeter thick base course, and on top of the base course, we have a 300 millimeter load plate and a static load actuator. We are now using a geogrid and we apply the load, and we can see that settlements are taking place at a certain stress level underneath the plate. This is represented by the blue line in the chart on the left side. If we are using a laid and welded geogrid, and in this particular case, it was a laid and welded 40 kilonewton biaxial geogrid, then of course this is represented by the blue line, but in case we are not using a geogrid, we can see the load settlement curve represented by the green line. And this line is showing us that the settlements are taking place at a much, much faster rate. And if we are now looking at a particular stress level, for example, 300 kPa, we're using the 2 geogrid layers, we are somewhere around 7 millimeter settlement. If we are not using a geosynthetic, then the settlements are already beyond 20 millimeter. So, and this is a result of the increased load spread using the geogrid, that the stress level that is transferred to the soft subgrade layer is reduced. Or in the other direction, we are not using a geogrid, we can expect higher stress levels which are transferred to the subgrade, and this leads to larger settlements. And looking at the stress levels which are measured by the earth pressure cells which are embedded in the sand layer, we can also see again that the unreinforced scenario gives us the highest stress level. Directly at the center of the load application, we are somewhere around 115 kilopascal. We are using 1 geogrid. We can reduce the stress level to something about 80 kilopascal. If we are using 2 layers, we can further reduce the stress that's transferred to the soft subgrade to approximately 70 kilonewtons. So also the addition of a second layer will further increase the load spread and will further reduce the stress level to the subgrade. A similar test has been carried out at the Technical University in Munich, very similar in its setup. We have a soft subgrade in a large steel frame box. On top of that, we have a base course. This was 30 centimeter and a 300 millimeter load plate. In this case, different to the previous one, we had a cyclic loading. Up to 1000 load cycles were applied, and the soft subgrade has a bearing capacity or an undrained shear strength of 30 kPa, which equals approximately a CBR of 1%. The test was carried out by using a section which didn't use a geosynthetic material at all. So this is the red column. Then one section just used the geotextile separator, abbreviated as GT3. Another section used only a layer of geogrid. This was a laid and welded geogrid made of polypropylene and 30 kilonewton biaxial strength, abbreviated as GT4. And the last section used a combination of the geotextile and the geogrid, a laid and welded polypropylene biaxial geocomposite with 30 kilonewton strength, abbreviated as GT5. Looking at the settlements that were measured by installing settlement packs and linear vertical displacement transducers on the top of the surface, the stress level underneath the plate was measured at 550 kilopascal. The diameter of the plate was equivalent to the thickness of the base course, and we can see a clear result of the settlements. If we are not using a geosynthetic at all, meaning no geotextile and no geogrid, we have the largest settlement, which are shown as 100% value. If we are using a geotextile only, GT3, we can already reduce the settlements by 40%. If we're using a geogrid, we can reduce the settlements by 60%. And if we're using the combination of the geotextile separator and the geogrid, we can reduce the settlements even to 70% compared to the settlements measured for the unreinforced section. So the best product to use is a combination of a separator and a geogrid reinforcement to reduce settlements and to improve the load spread in the fill. Another performance that we can measure in the lab is the improved shear resistance. So if we apply loads on our track, there is always a vertical movement that we can measure and a horizontal. And the horizontal movement always leads to a shear performance within the aggregate layer. So here we have a large-scale box test again, which was carried out at the university in Győr in Hungary in 2013. And it's called the so-called multi-level shear box test. You might have seen that in a few publications. In this particular case, the lower part of the box was filled with a silty subgrade, which equaled a CBR of 1.4%. The subgrade thickness was 50 centimeter. On top of that, we had a railway ballast with 400 millimeter thickness. There was no surcharge loading on top of the ballast, and 4 shear planes within the 400 millimeter ballast layer were measured. One at the interface to the subgrade, the second one 10 centimeter above this interface, 20 centimeter above the interface, and 30 centimeter above the interface, which is 10 centimeter below the upper edge of the ballast layer. A shear speed of 1.5 millimeters per second was used, and a shear distance of in total up to 80 millimeters. Different test sections were used, one without any geosynthetic at all, and the second one with a late and welded geogrid, a biaxial one with 30 kilonewton biaxial strength. What did we want to analyze or show in this test? We know from literature that the confining effect, which is a result of the interlocking of the aggregate particles with a geogrid, is the highest at the direct interface between geogrid and the aggregate material. The further we are moving away from the geogrid, the lower is the confining effect, because then the interlocking between the geogrid and the aggregate does not take place, and we can only rely on the interlocking between the individual particles, which is still influenced by the interlocking effect between the lower interface, but the confining effect will reduce the further we are moving away from this level. And so we can quantify the zones of confinement mainly into 3 categories. The first one is the lower one, which is the zone of maximum confinement, because we are closest to the geogrid. Then there's an intermediate area, which we call the transition zone. And the further we are moving up, we have a zone of minimum confinement. Here we can see the box and the typical cross-section. As I said, 40 centimeter of ballast was positioned on a sand leveling layer. Between the sand and the aggregate, we have the geogrid. And below, we have simulated a soft subgrade with an EV2 of 7 meganewtons per square meter. The cross-section, again, here we can see how the 2 boxes, we have an upper box and the lower box. The lower box is 1 unit. And the upper box is separated into 4 rings or frames, which we can loosen or fix together depending on which shear plane we want to analyze. So if we want to analyze shear plane number 1, which is the intersection or interface between the ballast and the subgrade, then all of the 4 rings are fixed, and we are moving the upper box against the lower box. You can see this with the 2 pushing forces. So the lower box is moved to the left and the upper box is moved towards the right, and then we are measuring the shear resistance in shear plane number 1. So if we are looking at the results of the individual shear planes, then we can see on the vertical axis the distance from the shear plane. So 0 is the interface between ballast and subgrade, and then we have the 4 different shear planes measured at 10 centimeters, 20 and 30 centimeters. And the result points were then measured in these 4 individual shear tests, and then a curve can be drawn to show the confining effect of the geogrid. But let's start first with the confining with the shear resistance of the unreinforced sample, which is represented by the black line. So we have a peak somewhere in the lower third of the complete subballast layer, which is similar in the reinforced case, but we can clearly see that the shear resistance or the pushing force is increasing as a result of the interlocking between the aggregate and the geogrid. So there's a very high increase in shear resistance, which of course is the resistance against lateral movement that we can measure. So as a result of interlocking, we can increase the shear resistance in the ballast or also in the subballast layer if we test that. Another test, which is also referring to a large-scale box test, is carried out at the Queensland University of Technology in Australia. This was carried out in 2018 and 2019. Again, a large-scale box, 1 meter width, and it was filled with 500 millimeter of a subgrade with a CBR less than 3%. On top of the subgrade, a subballast material was installed with 200 millimeter thickness. A load was applied to a 200 millimeter diameter plate of 550 kilopascal, and a dynamic load frequency of 0.33 Hertz was applied to the load plate to simulate dynamic load. The settlements were measured on top of the base course with linear vertical displacement transducers, and we can see a clear difference between the unreinforced sample as a result of the applied load cycles. So at approximately 120,000 load cycles, we can see settlements of around 92 millimeters in the unreinforced case. If we're using a latent welded geocomposite, we can reduce the settlements very visible to a value of approximately 55 millimeters. So there's 42% settlement reduction by using a latent welded geogrid. If we look at the vertical stress that was measured on the subgrade because some pressure cells were installed in the setup, we can see that at the same numbers of load cycles, we can reduce approximately 30% of the stress which is transferred to the subgrade. Again, this is due to the increased load spread within the base course material. Another large-scale box test was carried out at the University of Wollongong. This is a test which was based on a rail manufacturing cooperative research center project with the title Minimizing Track Deformation and Degradation with Geogrids on the High Frequency Cyclic Heavy Haul Load. The test was conducted using a large-scale cubical triaxial apparatus, and the diameter of the cubical cell was approximately 600 by 800 by 600 millimeter. And the box was filled with ballast. A concrete sleeper was tied to a section of a rail, and it was placed on the ballast layer to simulate a standard gauge Australian heavy haul track. The load and displacement in both transverse and longitudinal directions are monitored by inbuilt load cells and LVDTs. Vertical displacements throughout the sample height are obtained by settlement packs. And initially, 150 millimeter subballast layer is compacted at the bottom of the test, followed by 300 millimeter of ballast layer. The amplitude of the loading is between 25 tons and 30 tons at a frequency of 15 Hertz, which is equivalent to approximately 90 kilometers per hour. In total, 500,000 load cycles were applied. Here we are seeing the results. On the left side, we see a graph that shows the total vertical plastic settlements of the in the subballast and ballast layer. and we can see the results of the loads with 35 tons at 15 Hertz. These are the two upper curves. The continuous line is measuring the result with a laid and welded geogrid, and the upper dotted line is the result with no geogrid. Same at the bottom one. This is at the lower load at 25 tons, again at 15 Hertz with geogrid. The continuous red line and the dotted line is without any geogrid. So looking at these results, approximately at 500,000 load cycles, we can measure up to 20 to 30% total settlement reduction. And if we only focus on the reduction in settlements measured in the ballast layer, this is approximately 24 to 30% for these two loading scenarios. So substantial settlement reduction as a result of the installation of a laid and welded geogrid. Also in the same test, the same box was used to measure ballast breakage reduction. So as a result of dynamic load, usually what we can measure over the time is a reduction of the ballast particle size as a result of a crushing effect due to the dynamic loads which are applied to our ballast layer. So the ballast breakage index has been defined, which is shown on the left side. And the ballast breakage index is calculated as A divided by A plus B, where A is the area between the initial particle size distribution curve of the ballast and the final particle size distribution curve after applying the load cycles and after the crushing effect or the ballast breakage. And B is the area between the final particle size distribution curve and an arbitrary boundary of maximum ballast breakage. On the right side, we can see the ballast breakage reduction potential by using a laid and welded geogrid and by applying a load of 35 tons at 15 Hertz using no geogrid. These are the results for the top layer of the ballast, the ballast breakage index, the ballast breaking index for the medium area of the ballast and for the bottom area. So this was subdivided into 3 areas. The same for the section using a laid and welded geogrid. And of course, the maximum reduction in ballast breakage we can measure at the top of the ballast layer, because here the maximum load is applied. And if we look at those results between no geogrid and geogrid, we can measure a reduction in ballast breakage of around 15%, which is quite substantial. Also, if we are comparing the stress application versus the strain, meaning the settlement in the ballast, we can derive a resilient modulus of the ballast material. So looking at the same results from the same test, we can derive a resilient modulus of our ballast. So the dotted curve shows the resilient modulus if we are using no geogrid. The black line, the continuous line, shows the resilient modulus by using a laid and welded geogrid. And if we are using a geocomposite, which is a combination of a geotextile and the geogrid, we can see the resilient modulus as the blue line. And the result of that shows an increase of between 15 to 40% in track modulus increase by using a geogrid or a geocomposite. So again, our recommendation is to use a combination of a geotextile and a geogrid to have separation as well as lateral restraint and reinforcement. Here I'm showing you a case study which was carried out in New South Wales in Australia. This is a large-scale field trial in Singleton. And in this trial, we have a section that consisted of 300 millimeter ballast, which sits on top of a 150 millimeter subballast layer. And the subballast was positioned on structural fill, which provided a CBR of 30%. On the geogrids, strain gauges were applied, and also settlements were measured by installing settlement packs. Here we can see the results of the measured vertical deformation of the ballast in the left graph. In total, 4 different types of geogrids were used with different stiffness properties. And section A is the section using no geosynthetic at all. And depending on the number of cycles, which you can see on the horizontal axis, we see the largest vertical deformation of the ballast using no geogrid, and a substantial improvement, meaning a reduction in vertical deformation when we're using geogrids. Of course, this shows a wider range of performance with the different geogrids, and approximately vertical deformations of between 30 to 40% were measured by looking at the results of these 4 different geogrids. What was also interesting was that the main difference between these geogrids was the stiffness of the product, and it could be derived from the results that a 30% increase in geogrid stiffness resulted in a 20% reduced strain of the ballast. So there was a clear relation between the stiffness of the geogrid and the settlement reduction potential. The strains that were measured in the geogrid, which we see in the right graph, were between 0.5 and 2%. So they were all far away from a failure state, which of course is what we want when we are designing these structures. The serviceability limit state should be far away from a failure state, which was the case in this project. Now we are moving to Europe to show another case study. This is a rehabilitation project in Dolga Gora in Slovenia, which was carried out in 2008. And it was about a subballast rehabilitation. And the subgrade consisted of a high plasticity silt. And also we had a scenario where we measured high water tables. So of course, very critical conditions for a railway structure. The rehabilitation was carried out using a laid and welded geogrid, which was placed underneath the subballast layer, and the interface where the geogrid was positioned was approximately 1 meter below the surface of the ballast layer. Strain gauges were applied to the geogrid to measure the strain during the trafficking of the track with railway traffic. Here you see the strain gauges which were glued onto the laid and welded geogrid, and below the geogrid a geotextile separator was placed because, as I already mentioned, we have a soft, high plasticity, cohesive subgrade. Here we can see the positions of the strain gauges that were applied, and of course these types of installations usually take place overnight so that in the next day traffic can continue. We can see the installed geotextile and geogrid, and on top of the geogrid, a horizontal extensiometer was installed to measure the strain within the subballast layer. And the strain gauges on the geogrid were able to show the strain or deformation in the geogrid. The next slide shows us the strains that were measured in longitudinal direction at a depth, as I said, 1 meter below the top surface of the ballast layer. And the average strain that was calculated from the strain gauges applied to the geogrid is somewhere in the range of 0.15%, so on a very low level. This is in longitudinal direction. In transverse direction, it's approximately double of the strain, that's around 0.3, slightly less than that. Why is the strain in transverse direction slightly higher? Because we are missing the lateral confinement due to the embankment structure of our railway track. And in longitudinal direction, of course, we have the support of the ballast, which is then reducing the thrust force in our section. But both are on a very low level of strain, far, far away from a failure state. And that's exactly what we want to see. The stiffness of the geogrid should reduce the lateral deformation of the base course material, or the subballast material in this case. Here in these charts, we can see the strain that was measured in the geogrid and in the extensiometer. So the lower line is the geogrid strain, and the thinner line is the extensiometer measurement, which shows the strain in the subballast approximately 10 centimeters above the geogrid. And we can see that in the first days, there is a much higher strain in the subballast layer versus the strain in the geogrid. And this has to do with the rearrangement of the subballast until it really sits in an optimal position, and it interlocks with the geogrid in the best way, so that the particles are fully interlocking with the geogrid apertures, and the lateral restraint effect takes place. And we can see that this is achieved at this turning point. So there is a higher movement in lateral movement of the subballast material in the first days, and then optimum interlocking takes place, and we are not really measuring further deformations in the subballast layer. So if we are taking those settlements or the strains away out of the display of the strain measurements, so we took a zero measurement after 2 days after this construction was completed, then we can see that the strains in the subballast layer are maintaining on a very constant level over a period of 2000 days. So that's quite a long period, and we can really see that the geogrid does what it's supposed to do. It confines the fill material, it reduces lateral deformation, and the overall strains are on a very low level. So I'm moving to the end of my presentation, and I will show you some case studies. The first one is a case study from Australia. This is the Adelaide Metropolitan Rail Revitalisation Project, which was carried out in 2013. The project included a replacement of timber and steel sleepers with concrete sleepers and a replacement of ballast, formation repairs, as well as renewable and upgrade and construction of trackside drainage systems. Here we can see the installation of the geogrid on top of a separation geotextile. The next project, we are again in Europe. This is one of the biggest rehabilitation projects that at least I'm aware of. It covers a stretch of, in total, 200 kilometers. So this is a railway section that connects the capital of Romania, Bucharest, to the city of Constanța, which is located at the Black Sea coast. And the rehabilitation was required because of settlements that were measured in the railway track, and because of an upgrade of the track from 120 to 160 kilometers per hour. The EV2 requirement on top of the subballast layer was 80 meganewtons per square meter, and to improve the bearing capacity to the required bearing capacity according to the specification, a geotextile separator and a geogrid was installed on the soft subgrade. The installation took place with a train which is doing the full rehabilitation works, meaning it will excavate the old subballast layer, it will screen it to the requirement of the particle size distribution curve, then it will reinstall it on top of the geotextile separator and the geogrid, and finally also it will install a new ballast layer and it will lift the rail with the sleeper on top of the ballast. These trains are the so-called RPM trains, and it's very impressive to see these pieces of technology moving and doing a fast rehabilitation job. Here a close-up which shows the installation of the geotextile component and the geogrid, and the subballast material is installed on top. Another project which is from Germany, this is not a subballast reinforcement. This is a reinforcement on top of a piled embankment, because this section is running across an area which consists of soft peat. It's the railway section Berlin-Rostock, so it connects the capital Berlin to the city of Rostock, which is located at the Baltic Sea coast. And part of the section needed rehabilitation because a double track was constructed, and improvement of the subgrade was required because of the very soft consistency of the peat subgrade. So to reduce settlements and even more important, differential settlements, a piled embankment was constructed, and on top of the piled embankment, a load transfer platform reinforced with geogrid was installed. Here we can see the picture of the very severe conditions on site, a high water level. Due to the dark color, you can already get a feel of the soft subgrade, which is indicating the soft organic peat subgrade. Here we can see already the installed piles. The pile caps have been put into position. A sand leveling layer is installed to have a level surface for the geogrid installation. And the next pictures are showing the geogrids which were installed in transverse direction. This is a 400 kilonewton uniaxial geogrid. The first transverse layer is aligning the main stress direction transverse to the embankment axis. And within this wrapped system, we have a longitudinal layer also with 400 kilonewton in this particular case in main installation direction. And then if we are filling the soil on top of the installed geogrid, this side, which is wrapped outside of this package, is wrapped back into the structure towards the axis of the railway track. And here we can see the final picture of the fully rehabilitated section. Very nice part of this project was that monitoring was also carried out and settlements were measured. And settlements were measured over a period of 2 years, and 1 year after putting the railway traffic on top, only differential settlement of maximum 20 millimeters were measured, which were well within the specification and showed the robust construction performance, which met the requirements of the client. Another case study is showing the consequences of large floods, which we had in Germany in 2002. The river Elbe really carried a lot of water due to the flood situation. And this picture at the bottom left shows a railway embankment which completely collapsed because the water level even moved up to the surface of the rails. And we proposed a solution, rehabilitating this failed embankment by using a geogrid reinforced soil structure, using a steel mesh facing in combination with a laid and welded geogrid, which provided the fastest rehabilitation solution versus other methods like, for example, a concrete retaining wall. So we were able to show that the geosynthetic solution was the fastest and also the most economic solution to rehabilitate this railway embankment. Finally, and with that I will finish my presentation, I'm showing you an environmental performance analysis between a concrete retaining wall and a geogrid reinforced soil structure. So this was a project in Germany also where a geogrid reinforced soil structure was finally shown as being the most economic solution versus a concrete retaining wall. So an environmental performance evaluation was carried out based on a 1 meter length of the structure, a design life of 50 years, and of course the location Germany, which builds the boundary conditions of the prices and also the pollutants that were measured in this project. The level of detail in this project was that the consumption of fuel, diesel in particular, and the use of material was used to calculate the CO2 emissions. The site setup and the installation was taken into consideration. Material and energy flows were considered, and also the consumption of energetic and granular resources, meaning all the energy and granular fill materials required to construct this reinforced soil structure. The greenhouse effects were quantified as CO2 equivalents and acidification as a result of the construction works in terms of SO2, sulfur dioxide equivalents were calculated. The environmental performance evaluation makes it possible to assess the impact of pollutant emissions and resource extraction activities on the environment as a part of a life cycle assessment. The key metrics of this method are eco-impact factors, which measure the environmental impact of pollutant emissions or resource extraction activities in eco points per unit of quantity. I will not go into the details how many eco damage points were quantified for each of the impact categories. Due to the time limitations, I will just show you the result for the two solutions. So on the left side, we see the eco damage points, EDP, for the concrete retaining wall. So the higher this value, the more damage factor we can consider. So the higher the risk for the environment. So 100% value was considered for the original solution of constructing a concrete retaining wall. And by using a geosynthetic reinforced soil structure, we can reduce the ecological damage points to only 1/3. So we have 2/3 reduction in ecological damage points using a geosynthetic reinforced soil structure, which of course are quite substantial. With that, I will close my presentation. The presented results from laboratory and field trials have shown that the installation of geogrids and more important, the installation of geocomposites in railway track applications contribute to the following. First of all, subgrade stabilization and bearing capacity improvement, improved load distribution, ballast and track settlement reduction, the increase in resilient modulus of the ballast, which makes it more resistant against deformation, and also geocomposites were able to reduce ballast breakage and to increase the service life of railway tracks. So the benefits are, as I mentioned, increased service life, reduced maintenance cost, reduced project cost, because as I mentioned, the geogrids and geocomposites can reduce the thickness compared to unreinforced sections. And as the last example showed, geosynthetics can help to reduce the environmental impact in projects and to reduce the carbon footprint. And with that, I thank you for your interest. And yeah, we might have a few minutes left for questions and answers. Back to you, Siamek.
Perfect. Thanks very much, Jorg. And we've got maybe around 6 or 7 questions. We might not get to all of them, but let's just start answering a few of these questions. This one about using aggregates. So compare with like other types of material. So the question is, the geogrid works the best with aggregates or crushed rock to mobilize interlocking forces. What if we have only sand placed over low CVR subgrade? Is using a geogrid still beneficial?
It is, but it's similar like with geosynthetics. There is a difference in different geosynthetics. I already mentioned that the stiffness property of the geogrid will have an impact on its performance, and the same we have with soil. So if we are using a lower quality soil, like in your example, if we are using sand instead of a crushed stone, this is a reduction in stiffness of the material. The geogrid will still provide benefit because we have the reinforcing effect that we can quantify for this material, but we are reducing the interaction efficiency between the sand and the geogrid, where we have a interlocking effect with granular larger stone sizes between the aggregate and the geogrid. We are now relying more on a frictional interaction if we are using a finer grain sand fill material. And friction is less efficient versus interlocking. So yes, there is a benefit, but to a lower extent compared to a crushed aggregate.
Yeah, and I think with that, you have probably answered this other question, which is quite similar, asking about rail lines supported on highly reactive clays.
Yeah, of course, highly reactive clays always have a potential to heave, so to have a lift up of the fill material, but also at the same time they have a potential to transfer horizontal shear forces into the upper layers. And as I already showed in the large-scale lab test, the geogrid will reduce lateral deformation, and this will counteract the lateral deformation that highly reactive clays are imposing to railway structures. So using a geotextile separator, first of all, that separates the fine-grained subgrade from the coarser fill helps, but the geogrid will then reduce lateral deformation as a result of the highly reactive clay soils. So geogrids are very efficient for these types of boundary conditions.
Yep. The next one is about different grades of geogrids. We normally come up with a required reinforcement force in our calculation. Do you think, or would you suggest using more lower grade layers or fewer higher grade layers of geogrid?
Yeah, I think one of the large-scale lab tests showed that including more layers helps further reducing the stress that's transferred to the subgrade as a result of an increased load spread angle. But also there's a limitation. We shouldn't space the geogrids too close together because that will also have an impact on the shear behavior within the fill. So what we are usually recommending, and I think that's common sense in the geosynthetic industry, approximately 150 to 200 millimeter should be the minimum spacing between the geogrids. Then we get the best result. And also, just as a rule of thumb, we can say that the softer the subgrade, the higher the strength of the geogrid should be to absorb the tensile forces which are developing as a result of the loading on top. So yeah, the softer the conditions, the more severe, our recommendation is to install a higher strength geogrid, which has more resistance against the deformations.
Sure. And last question before we go to Jake for a quick wrap up of today's webinar. Somebody asked about some more references for further studies. If you know any sort of good references that you can introduce, please.
Yeah, I'm happy to share those. I can send them to you, and you can
sure.
pass them on. Yeah.
Perfect. Jake, we come to you with a quick wrap up, maybe introduction to NAWA Asia, and so I'm sure, like this last question, there are people in our audience who want to know more about the the ways that they can reach out to you guys and get technical support, or if they have any questions about the material that was presented today. Jake.
Yes, thank you. Well, thank you, CMAC, for inviting us today. Letting us do our seminar, and thank you to all the IGS members for watching. I see there's people from all over the world that have come to join. Thank you, Jorg, for the presentation. Jorg and I, thanks to COVID, find ourselves not in Asia today, but in the UK and in Germany. So very early start, but I'd really appreciate it. Yeah, just wanted to say that NAWA, everybody here is aware of NAWA. NAWA Asia is been established in Malaysia for about 11 years now. I've just put the website there. If you have any inquiries, if you want to have any further questions, you can email asia@nawa.com. NAWA in Australia, Southeast Asia, works closely with partners. So our two biggest partners really are in Australia is Geosynthetics, and in Thailand is Vigamerger. Any inquiries about geosynthetics or further questions about today, I said you can email us and we will work with our partners and get back to you. Just the final comment I would make, just some practical information. Our geogrids are produced in Europe, and we have our facility in Malaysia producing a range of other geosynthetics. We're in a situation globally with shipping issues, which I'm sure people are aware of, but it is impacting the flow of resins, raw materials, and products across the world. The state of the shipping is a challenge for the geosynthetic industry. So when people are looking at planning projects, etc., should consider the impact it's going to have on supply, because it is certainly leading up to Christmas. It's a key issue. But yes, thank you very much for having us today, CMAC. It's been a pleasure.
Thank you, Jake. So before we wrap up for today's webinar, I just encourage everyone to attend the November webinar, which is going to be on the 17th of November. The topic is reinforced soil walls. So that would be our next event. Thanks again, Jorg, for your presentation today. And we had a lot of people actually thanking you for the presentation. Very great presentation. And Jake, for you being with us a very early morning, your time in the UK. And I know it was still early for you, Jorg, this morning in Germany. Thanks everyone for joining us today from around the world. As Jake said, we had people from the Middle East, from Asia and Australia, New Zealand. Thanks everyone, and we see you in our next event, 17th of November. Thank you.
Thank you. Bye-bye.
Bye.